Today we're going to talk about acids and bases and the theory behind what makes an acid be an acid and a base a base. If we're dealing with acids, acids are acids because they have hydrogen ions in them. Bases are bases because they have hydroxide ions in a solution that is basic. So if you're looking at HCl, for instance, HCl is a common acid. When it's not in water, it's a gas. But as soon as you put it in water, it's going to ionize. And when it ionizes, it produces a hydrogen ion and a chloride ion. Both of those dissolved in the water. That hydrogen ion is what makes an acid be an acid. Without that hydrogen ion, we don't have an acidic solution. And that's important to remember later when we're talking about the strength of acidic and basic solutions. A base, on the other hand, NaOH, when we put that in water and it ionizes, it is going to end up forming whatever the metal is that it's combined with, and OH minus, the hydroxide ion. Again, both of these are dissolved in the water. And for it to be a basic solution, if it doesn't have that hydroxide ion in the solution, it's not going to be basic. So again, when we talk about relative strengths of these acids and bases, it'll be important to remember that. Now, the Bronsted-Lowry definition goes a step further. The Bronsted-Lowry definition says that we would want to always show an acid reacting. There's always going to be something acting as an acid and something acting as a base. So if we have HCl acting as an acid, and a Bronsted acid is something that donates a hydrogen, then we're going to have HCl acting as the acid, water acting as the base. Bases are, in AP we call them dirty, nasty hydrogen stealers, but they accept hydrogen ions. So when this reacts, the HCl, the acid, is going to give away a hydrogen, so it's going to be left with just the Cl minus. And who's it going to give that hydrogen to? The only other thing in the solution, and that's the water. And when that happens, we form the H3O plus ion. Now, this is such an important ion, it's given a special name. This is called the hydronium ion. Hydronium ion. A base, then, is going to be a substance that reacts again and takes on a hydrogen ion acceptor. And let's take NH3, and this is going to be a good example and show you why NH3 can act as a base. It doesn't look like it's a base because it doesn't have a hydroxide on it. But if we put it into an aqueous solution, put it into water, now you're going to see me draw this type of arrow for this particular substance. That's because ammonia is a weak base, and I'll talk more about that in just a moment. But we have the ammonia reacting with the water. Again, ammonia is going to be a dirty, nasty hydrogen stealer, and it steals hydrogen from the water. So what it ends up forming is something we've seen before, the ammonium ion. And what it leaves behind after it takes one of the hydrogens away, it leaves OH minus behind from the water. So that is an example of a Bronsted-Lowry acid-base reaction. Now, in this reaction, again, something always acts as an acid and a base. Something always acts as a base. In this case, ammonia is the base. So water must be acting like the acid. This brings up something called an amphoteric or an amphiprotic substance. It's a substance that can act as either an acid or a base, and water is one of those substances. Water can give away a hydrogen and form OH minus, or it can gain a hydrogen and form H3O plus, amphoteric or amphiprotic. In addition, formed in a Bronsted-Lowry acid-base reaction is something called a conjugate acid and a conjugate base. A conjugate acid is formed when the base gains a hydrogen ion. So if we look up in our first example, the base was water. When it gained a hydrogen ion, it became H3O plus, so this is our conjugate acid, and I'm just going to label it Ca. A conjugate base is formed when an acid has donated or given away a hydrogen. So the acid in this first example was HCl. So once it gave away its hydrogen, it formed Cl minus. That's going to be the conjugate base, which I'm going to label as Cb. So why don't you pause for just a moment, pause the video for just a moment, and determine in the next example, the one with ammonia and water, what the conjugate acid and conjugate base would be in that example. So hopefully you did that. And as it said in the definition, the conjugate acid is a base that has gained the hydrogen ion. The base is ammonia. When it gains a hydrogen ion, it forms NH4 plus. So that NH4 plus is going to be our conjugate acid. The conjugate base is a species formed when the acid, water in this case, has donated a hydrogen. And after the water donates a hydrogen, it's going to be OH minus, the conjugate base. So if you're asked to find the conjugate acid of HSO4 minus, remember conjugate acid gains a hydrogen, so we have to gain an H plus to form the conjugate acid. If we gain an H plus, this will become H2SO4, and think about it. If we gain not only the H but also a positive sign, that negative and positive will cancel and our resulting species will be neutral. See if you can do the next one yourself real quick, HPO4 2 minus, finding its conjugate acid. So hopefully you did that, and not only did you gain a hydrogen, so you formed H2PO4, but you also added a plus. So if you had two negatives and now you've got a positive, that's going to end up being simply a negative charge. The conjugate base, remember, is going to lose an H plus. And it's going to become more negative. So if we have H2S, losing that H is going to form HS. In addition, it was neutral. Now it's going to become more negative because it lost that H plus. So we're going to form HS minus. See if you can do HPO4 2 minus really quick, remembering to lose an H plus from that species. Hopefully you came up with PO4 after you lost the hydrogen, and since it became one more negative, the charge on this now is going to be 3 minus. So that's how you're going to find conjugate acids and conjugate bases. Now strong acids are acids which ionize or dissociate. They break down completely. There are some strong acids here, HCl, HBr, HI. These are the ones that are recognized by AP. H2SO4, HNO3, HClO4, HMNO4, H2CrO4. These are the 7 strong acids, and these are the only 7. So if there's any other kind of acid, it's going to be a weak acid. If it's a strong acid, we're going to show it with what I sometimes refer to as a strong arrow. It's an arrow that shows that this reaction happens completely. This is going to be aqueous. We put it in water, and we're going to show it breaking down into H plus and Cl minus. Both of these are aqueous as well. Make sure you put that on there. Now the reason this is strong, it reacts completely, and let's say that we start out with 100 HCl's. When we get done, we are going to have this reacting completely. We'll have 100 H's and 100 Cl's. So we're going to have the maximum H pluses possible. So that's why it's a strong acid. Now let's look at how we would do the weak acids. They're done the same way in ionization. We're just going to use a different kind of arrow. HNO2 is again going to be referred to as aqueous. Since weak acids do not completely ionize, we're going to show with this arrow, it's actually an equilibrium arrow, but we'll discuss more about that in AP. We're going to show that part of them are reacting, but part of them are not. And that's what that double arrow is referring to. They're actually going back and forth, but we don't have, at any given time, for instance, we'll have our H plus and our NO2 minus. Simply take off the H plus and leave the rest of it behind with a negative charge. But at any given time, as I was just saying, let's say we started with 100 HNO2s, we might have in solution at any given time 5 hydrogens. Now this is not mathematical or anything, I'm just pulling these numbers off the top of my head just to show you that any given time we might have 5 hydrogens, 5 NO2s, 5 nitrates, and only maybe 95 of the HNO2s instead of 100. My point being, we don't have very many H pluses in this solution if only that many have ionized. If we don't have very many H pluses, we don't have a very acidic solution. So that's why it's a weak acid. Same thing we're going to do with CH3COOH. This is the only one that you're going to have to memorize what happens. For the rest of them, the H comes off and everything else is left behind as a negative. This one, the same thing happens, but what's weird about an organic acid like this acetic acid is that the H that comes off is at the end. So it is weak still, so we're still going to use a weak arrow, showing that not all of it is reacting. It's not a completion reaction. We don't get 100% of these CH3COOH molecules ionizing to form an acid, or ionizing to form H+. So what happens is we'll get the CH3COO off as a negative, and the H+ will come off as well, and that's going to be aqueous as well. And make sure, I almost forgot it up here, but make sure you put those aqueuses after it because they're in water. So again, the only difference between a weak acid and a strong acid is what kind of arrow you use. Otherwise, it's going to split apart the same way. Now, strong bases are ones which also ionize or break down completely. There's a rule. You don't have to memorize the strong bases like you do the acids. The rule is that hydroxides of groups 1A and 2A, except for magnesium hydroxide, are going to be strong. So examples would be NaOH because Na is in group 1A, KOH because K is in group 1A, BaOH2 because barium is in group 2A. All of those bases from metals in groups 1A and 2A are going to form strong bases except for magnesium. So if it's a strong base, once again we're going to put that it's aqueous. We're going to use our strong arrow, our completion arrow. It reacts completely, and we get K plus and OH minus left behind. You're going to take off the OH minus, and then you're going to leave the metal ion, the metal cation behind. If it's got more than one hydroxide, you have to show that. For instance, barium hydroxide. It is strong. It's going to react with a strong arrow, and we're going to form the barium ion. Now watch it in this case because barium has a 2+ charge. Notice that it's combined with 2 hydroxides, so it's going to be a 2+ charge. You can get that from the periodic table as well. And it leaves behind, look at where I'm putting the 2, in front of the hydroxide. So make sure you show it like this. If there were 3 hydroxides, you put a 3 in front of the OH minus on the product side. So just make sure you're paying attention to the charge on the metal and how many hydroxides you have. If it's weak, then we, once again, are going to have to show that it's using a weak arrow, an equilibrium arrow, an arrow that shows that not all of it is going to completion. Ammonia is one of the types of substances we have to show combined with water, or we can't explain why it does what it does. And I guarantee you this is going to be on most of the worksheets and on the test that you do, because it's such an often used base in AP. We want to make sure we're really familiar with it. So it is weak. We're going to put double arrows, and we've seen this on the previous page that we end up with NH4 plus and OH minus. On the previous page I didn't put aqueous, but you probably should go ahead and do that, even though water's shown over there on the left hand side. But okay, the last thing I want to show you is what happens if you have a polyprotic acid, an acid that has more than one ionizable hydrogen. If you have a polyprotic acid, what you're going to show is one hydrogen coming off at a time. In the case of H2SO4, look back up at your list. It does show H2SO4 as one of our strong acids. So what kind of arrow is it going to get? Exactly, it's going to get a strong arrow to start with. And when it reacts, it's going to form H plus, and then think about what would be left over. It's like forming a conjugate base. We're going to have HSO4, and it's going to be more negative since it lost that H plus. So HSO4 negative. We want to keep reacting it until we don't have any hydrogens left. Do we have hydrogens left in there? Yes, we do. There's an H still left with the HSO4, so we're going to keep reacting. Now, is HSO4 minus one of our strong acids up here in our list up at the top? And we look, no, it's not. There aren't any ions that are strong acids or bases. So what kind of arrow are we going to use? Yes, our weak arrow or equilibrium arrow. We're going to show that one more hydrogen was taken off, and that is going to leave behind just SO4. And think about it, if we took off another H plus, it's going to become even more negative, so this is going to be a 2 negative in charge. Since there are no more hydrogens left in sulfate, we are done with sulfate. We're done with this particular acid, H2SO4. So look at the last example. H3PO4, it's polyprotic again. And by the way, up here, I know I probably shouldn't take points off of your paper if you leave them off whenever I forget them sometimes in the notes, but I'm going to anyway. So H3PO4 is going to be put in water. It is not one of our strong acids. Look up at the list and you'll see it's not one of our strong acids. So we're going to start out this time with a weak arrow. And when it reacts, it's going to pull off one hydrogen and leave behind just 2 hydrogens in the acid. And since we took away an H plus, it's going to become more negative. Since we still have hydrogens left in this species, we're going to keep going. So once again, we have, it's not a strong acid, so it's going to be the weak arrows again, the equilibrium arrows. We're going to take off a hydrogen and leave behind something that has one less hydrogen, HPO4. It is more negative, so it's going to be a 2 negative this time. It still has hydrogens left, so we're going to, looks like we only have 1 hydrogen left, so we should be okay to do this just one more time. H plus, take away the final hydrogen, PO4, and since it's, again, 1 more negative, this will be 3 minus. So that would be the ionization of this polyprotic acid. Now I will tell you, before you panic, both of these, if you get a polyprotic acid on a worksheet or a test, these will be extra credit opportunities for you. If you can show the ionization of these types of compounds, these types of acids, you can get extra credit for it.